some of my students, I thought it would be a good idea to take a really close look at decimals and their relationship to fractions. Making sure that something is really understood. Imagine we got two containers here and we're going to put some marbles in them, and what colour should we pick on that? What about that? That does not work very well. Let's try this. That would do. Okay, now imagine these being perfectly round. We've got a marble there, a marble there, one there, one there, and one there. So in fact we have got 5 marbles. Now I'm not going to bother to count them. Alright, lots and lots and lots of marbles. You'll understand in a moment what the connection is and what I'm driving at. These are a lot more than 5, so I'm going to call the count A. Whatever it is, that is the value of the count. Right now, that value there is greater than 5. We've got more in. So if we got more in, these must be smaller. You know, the diameter of each of these will be less than the diameter of those. What's the connection of this idea, this concept, to that of fractions? Look, we have to get more in here to fill up the container. So we need more of these than we do of those to make a complete one container. Well, the connection to fractions, we have a count, numerator, proper word, and we have size indicator. My wording, I'm going to put IND for indicator. Now this number here, if this number is quite a size, for example 63, and we had a count of one of them, because that number there is greater than the number of 5, these, because you have to fit more of them in, must be smaller than those. Do you see the connection between the image and the idea of the denominator? The bottom number, if it is a great number, it is the actual item that you're counting is smaller than the item on this side. Very important. So as this number here underneath, the size indicator, increases and increases and increases, each one of the items gets smaller and smaller and smaller. Some people are confused by this. Hopefully this will sort it out. Pictorially, remember it. More in means smaller. The top number is the count of how many you've got. The bottom number indicates the size of what you are counting. So what is the link between fractions and decimals? Now, I'm not saying how do you calculate them, I'm saying what is the link? Well, we know what a fraction is. Suppose we have here, write it in decimal form, 2.562. What is this really? This is whole number 2, and you've seen me do this before. Write it like that. Not normally done, but I'm choosing to write it like that. It is correct. Now that is put with the 5, and the size of what we're counting is tenths, which is also put with 6. The size of what we're counting is 100th. Put with 2, the size of what we're counting is, each time you go down it's an extra naught. 2 noughts, so you've got 1, 2, another naught, next size. This here is your fraction. This here is a fraction, but it's written differently. They are the same thing. It's just a different way of writing fractions. Now they say convert a fraction into a decimal. Let's consider just making some numbers up. 5 over, go on, 15. Let's say divide the bottom into the top, and it gives you the decimal. Why? Why do they say that? Because they're not telling you the whole story. Whole story is, notice this one here, whole number, 1. Well, what they want to do is to convert it to 1 down here. Alright? That's what they want to do. Remember, it's not normally written. 2 is normally on its own. I don't normally write that. This will not normally be written. But they are actually converting that value there to 1. So what we end up with is 15 as a denominator, 5 as the numerator. Divide that by 15. Now because you divided the bottom by 15, you have to also divide the top by 15. It is maintaining the ratio of those numbers to each other. You know, like half, exactly the same as 2 over 4, exactly the same as 4 over 8. The ratio of those numbers are the same to each other. So we need to maintain the ratio of these numbers to each other. Now that would give me the 1, which is not normally written, and now you have the top divided by the bottom. This is why they say what they say. They don't necessarily explain it as to why it's that way, but this is actually why they do it. Okay, let's focus on decimals. Before we start, you're bound to get asked to convert fractions to decimals. There are some you need to commit to memory. First one is the half. Well, we know that that is 0.5, which is 5/10, alright? Which is the same as if I divide that. Oh, that would divide into that by 2, right? So if we convert that to 1, wait a minute, divide by 5, yeah. That will give me 1 on the top, divide the bottom by 5, and that will give me 2 underneath. Right? So it is indeed 0.5. The next one you need to know, commit to memory, is a third. Now that little baby here is 0.333, and the 3's go on forever and ever. Normally you round it. Now here's the thing with decimals. If we know that those 3's go on forever, now if we round it to 3 decimal places, 0.333, always say to 3 decimal. Always state that. Why? Why do you always state that? If you don't, they think that is the actual value that you're looking at. Now there's a problem there, and I will come back to that in a while. A third is 3's that go on forever. Now if you were to write it like this, and you can choose to put one there, a line over the top, or if you go here, you can put a line over the top there. You know, it tells people, this little signal here tells people that the 3's go on forever and ever. Very important. Now let's suppose we have 0.454545, and they go on forever. Well, you put a line over the 2 digits that go on forever. That tells people this here is not quite as written, that the 4 5's go on forever and ever and ever and ever and ever and ever. A third is that. Remember it. Next one, quarter. That one, 0.25. Now, because this one here stops definitely after the 5, you can put zeros if you want after it. It won't change the value. It stops at the 5. They call it terminating, stops. If a decimal stops or terminates, it is definitely a fraction. If it repeats on and on and on and on and on, whether it be pairs of numbers or single digits, it is also a fraction. If the numbers never repeat and the decimals keep going on, I'll give you an example. Shift pi. Give me the decimal, thank you. There's absolutely no repeats. Believe me, there's no repeats. It stops on the calculator because the calculator can't do any more decimal places than that. Okay? It goes on forever and ever with no repeats. That is not a fraction. It's what they call irrational number. It's got a proper name. Fractions are called rational numbers. Now that doesn't matter. Just remember that fractions either terminate or you get repeats forever and ever and ever and ever. So we have a half, a third, a quarter. Now we have an eighth. 0.125. That is half of that. So if you can't remember what an eighth is, and you can remember what a quarter is, just multiply it by half. So we end up with 0. Half of 2 is 1. Half of 5 is 2.5. Half, 0.5. A third, 0.333. It goes on forever, never, never, never. Quarter, 0.25. An eighth, 0.125. Fix those in your mind. Now we need to talk about rounding numbers, digits. It doesn't have to be decimals. Look, if we have 2, 3, 6, 9 as a whole number, if you like, I'll put the decimal point, and I want to round that. They call it significant figures, by the way, this particular thing. When you're doing that, it's the numbers that have the greatest effect. So if we want it to 2, I'll put sig, figures, alright? Abbreviated, abbreviated. 2 significant figures, 1, 2. There's your cutoff. Now we round this. If it is greater than, if the value you're looking at is greater than or equal to 5, 6 is greater than or equal to 5, we round that up. So it becomes 24. Now 2 significant figures, that's the cutoff point. So we put a 0, 0. If you like, you can put the decimal. So to 2 significant figures rounded up, right? So it is rounded. To 2 significant figures. Important rule: to the right of the cutoff, if it is greater than or equal to 5, you round up. If it is not greater than or equal to 5, you don't change it. The rule is the 5. If it is greater than or equal to the 5, you change it. Very important. Rounding of decimal values. What should we go for? 2.6947. Alright, let's change the colour. Shall we change it? Does that show up? Yeah. Okay, suppose the cutoff point is there. to the right, the single digit immediately to the right of the cutoff point is 4. So in this case, x, or if you like 4, is definitely less than 5. It's certainly not equal to 5, it's less than 5. So if that is the case, we don't change anything here. We just write 2.69, but we must state 2 decimal places. Must state it, because that is not the same as that. This is saying it is not an exact value. It is telling them that there is a change, so if they include it in other calculations, it could introduce an error. Right, now let's look at this again. Let's go back to our green. 2.6947. Suppose the cutoff point is there. So we want it to be to 3 decimal places. You look immediately to the right. Imagine that being x. So the question mark, is x greater than or equal to 5? Is that greater than or equal to 5? Yes. So we change the 4. So we end up with 2.695. We round it up by 1 place. But then we say to 3 decimal places. Again, very important. Rounding is something that gets people into trouble sometimes. It's fairly straightforward once you get used to it. That is the golden rule. The number immediately to the right of the cutoff, you look at this. Alright, the next bit is higher than functional skills, perhaps the top end of GCSE, but I want to include it. Suppose we have a decimal where I'll just use decimal values, 0.3434, and they go on forever. There's that little thing there telling me it goes on forever. Alright, so we set x equals 0.3434. We can do that. We've declared it. We've now said that x has that value. Now because these 3 4s go on for never, we need to get rid of them some way. This is true equals if I multiply the left of the equals by 10 and multiply the right of the equals by 10, the equation is still true. You know, this is true. Alright, now look, if I go 10 times x equals 10 times 0.3434, go on forever, it is still true. I'm going to call that equation 1. I'm going to call that equation 2. So when I say equation 2, you know I mean this one here, which in fact is, multiply that, oh no, should be by 100. Sorry, wrong. Let's correct that. Oh. 100 times x equals, you'll understand why in a moment. That's better. Right, now, so this one here, equation 2, becomes 100 lots of x, and this one here, we in fact move the numbers to the left by 2 noughts, the numbers move to the left by 2, the decimal point stays still. So we end up with 3, 4, 0.34, where they go on forever. So I'll call that 2a. Okay? Now, if I do equation, whoops, whoa. That's meant to be 2a, subtract from that, whoops, equation 1, we end up with, now equation 2, 2a is this one here, look. Alright, I'll write it this way. That is the same as this. So that is there, that's equation 2a. Now I said subtract from that equation 1. This is equation 1, 0.34, right? So it is 0.3434. That's equation 1. And I want to subtract one from the other. And this one here is that one. This one here is that one. If you multiply the left by 100, you have to multiply the right by 100. So 0.34 reoccurring becomes 34.34. So that is true. Right? That is true. That is true. Just subtract that from that. 1x from 100x gives me 99 lots of x equals, and magically all the decimal points disappear. And let me lift that up a bit. So what we end up with, this one here, 99x equals 34. Divide both sides by 99. You know how this works. Divide both sides by 99. I'll do that. Look, 99x over 99 equals 34 over 99. Those cancel out, so we end up with the x, which is the actual fraction, is equal to 34 over 99. Now many of these you'll find will have 99 at the bottom as the denominator. That is the fraction, has exactly the same value as that decimal. Watch it a few times. It's an exercise in thinking for those that have not come across this before. Some of you will never need to use it. Some of you could well need to use it. But it is a good exercise in thinking and understanding relationships. That's the whole point of mathematics for some. It helps you develop the ability to spot relationships and be able to play with those relationships. This is what we've done here.